Все они иностранцы. Они приехали из Америки, из Франции и из Чехии. Здесь наша основная цель, мы будем рассказывать, что наука — это весело, это легко. Если есть среди нас учителя? Да. Круто. Наша основная здесь цель — показать, что науку можно делать из простых вещей тоже. Не нужны какие-то лаборатории. И первый сегодняшний наш спикер, он приехал из Франции. Его основная фишка, его история в том, что он любит, помимо науки, он любит еще ездить на велосипеде. На велосипеде он проехал больше 40 стран, прям на велосипеде, да? И цель его этих путешествий была в том, что он заезжал в каждую страну и собирал очень разные эксперименты от учителей тех стран. И сегодня он вам покажет выжимку из самых интересных экспериментов, которые он собрал из многих европейских стран. Встречайте Майкл Грегори. Hi, Michael.
Hello. Thank you for that introduction and welcome.
Те, кто не понимает на английском, я думаю, вы получили микрофоны, вы можете их уже включать. Те, кто понимает английский, супер. Я желаю вам наслаждаться его выступлением. Раунд оф applause.
It's great to be here in Kazakhstan, and great to get to share some of my favorite experiments with you. So, I'm a science teacher in Paris, France, but in my free time, I love traveling, looking for new experiments in different places around the world. And today, I'll be showing you some of my current favorites that I've learned from different places. As you'll see, all the materials I use are very simple, so that they should be accessible to schools and in the homes in most places. So as you watch some of these experiments, my challenge to you is to think of some of them that you can try and repeat later to impress friends, impress families, go to school on Monday, impress your teacher. I'm going to show you some experiments from different countries, from Spain, Bulgaria, Ghana, Germany, England. To start off with, here, I have three very simple objects. I have a bottle with some green water in it. I have a flashlight and a tape measure. And the only reason I'm using these objects is because I'll be using them later on for other experiments. To start off with, I want one volunteer, and you don't need to come on stage, just stay seated where you are, but one person who wants to volunteer from your seat to help out with this. I saw your hand go up. So I want you to pick the long one, the short one, the medium one, or the short one. So pick this one, this one? The flashlight? Perfect. So I want you to think about the flashlight, concentrate on it, and with the power of your mind, try and get it to swing back and forth, with the others swinging as little as possible. Do you think you can handle that? Okay, so let's see if she can get the middle one swinging back and forth. Can we give her a round of applause? Now, that seems like magic, but of course it's science. So let's see if we can get someone else to get the long one to move. So I want one other volunteer to try and get the long one to move. Okay, you'll be my volunteer for that. And so stare at it and try and get the long one moving. And as we're trying to get it moving, this experiment is one that was shown to me by a professor in Valencia, Spain, called Chantal Ferraro-Roca, who's also a big fan of experiments, and we see that one's moving back and forth. So let's give him a round of applause. We saw the medium one move, the long one move. How about the short one? Let's do all that together because it's a little bit harder. So everyone, look at the short one really hard, and let's see if the short one can move. Way to go, everyone. Now, of course, this isn't a magic show, it's a science show. So we need to try and think of a scientific explanation for what's going on. And let's look at what we see here. We see different objects with different lengths of string. Now, if I move it wildly, they move at different speeds, right? Which one moves the fastest? The shortest one. And which one moves the slowest? The longest one. Okay, so if we use that, and if I look at the speed it's swinging, so let's look at, say, the long one, and it'll swing forwards and backwards, forwards and backwards. And if I move my hand at the same time, we see the long one swings more than the others. Similarly, if we look at the short one, we say back, forth, back, forth, back, forth. We get just the short one moving. So if your attention is on the object rather than my hand, then it's quite easy. If I only move it a bit, let's try for the middle one. So let's say when it goes forwards, back, and you notice the movement there, but not the timing of my movement up there. And that's a demonstration of the phenomenon of resonance. Just like kids on a swing set, or just like how sound is produced in musical instruments. So this simple setup can help us understand resonance. And I'll be using these other objects in just a minute. That's how what? Exactly. And it's good to make you think that you can do magic to start off with. So the next experiment is one that one of my students in Paris taught me. And other than traveling to look for experiments, I look to my students as one of the biggest sources of inspiration. And I always tell them, try and surprise me, try and wow me, try and teach me something new. So this experiment that was taught to me by a student in Paris about 8 years ago, I've now shown to people in over 40 different countries. So all of the kids who are in school here, I want you to show your teachers experiments, and maybe they'll teach other people as well. So for this one, I have a bottle of water, which is handy because it gets hot and thirsty on stage under the lights. And I have a couple of drinking straws. And some paper. And that's all I need for this one. I'm going to take the straws, rub it against the paper, and I want everyone to make a prediction what will happen next. So for the prediction, I'm going to place the blue straw on the water bottle, and I want everyone to predict when I bring the pink straw near the blue one, do we expect the blue one to be repelled and pushed away, attracted and pulled near, or do nothing? So if you think it'll be repelled and pushed away, put up your hand. Okay, there's a couple of people who think that, but not so many. If you think it'll be attracted and drawn near, put up your hand. About the same. If you think it'll do nothing, put up your hand. And nothing's actually a good guess, because if this experiment fails, that's what happens. And it doesn't always work. But let's try it out and see. So, and I think I spent too long talking because things discharged. So anyone who voted nothing, good guess. So let's try that one more time. Okay, blue straw in the bottle, just like before. Pink straw going near. Okay, and we see this, that the straws are attracted. Now I'm going to bring the piece of paper near. Same prediction. I want you to predict if it'll be attracted, repelled, or nothing. Who thinks it'll be attracted? Put up your hand. Who thinks it'll be repelled? Put up your hand. Okay, a lot of people think repelled. Who thinks it'll do nothing? Put up your hand. And I'm actually quite curious myself, because the first part didn't work out how I expected. And here it's also attracted. Now, I'm going to repeat that one more time with two different straws, just to see if we have the same result. So this time a red straw and a yellow straw, and the color shouldn't affect the material of the straws. Yellow straw on top, red straw coming near. Oh. Both attracted and repelled. Okay, so the explanation of why this is happening, when I charge the straws, we're transferring static electricity. So all materials are made of charges, positive and negative charges. And sometimes the charge can move. Sometimes a material will have a stronger pull on electrons. In this case, the paper is pulling electrons away from the straw, and the straws should be left both with a positive charge. And there we see they're repelling each other. So they're pushing each other away because they have the same charge and similar charges repel. The paper has an opposite charge, so it attracts. Opposite charges attract. Now, my hands, these are uncharged. This is the hardest question yet. If I bring my hand near the straw, my uncharged hand, neither positive or negative, do we think it'll attract, repel, or do nothing? If you think it'll attract, put up your hand. A couple of people. If you think it'll repel, put up your hand. Very few people. If you think it'll do nothing. Okay, a lot of people think it'll do nothing. And we can clearly see it's attracted. So, we might think I just have attractive hands. But can I get a volunteer to come up so we can check if... Okay, you're right near the front, so come on up. And what's your name? Noli? Nolali? Nolali? Okay. So, I want you to see if you also have attractive hands. So see if the straw is attracted to your hand. And we see he has attractive hands. Let's give him a round of applause for having such attractive hands. And you can go sit back down. And what's going on here, it's not that our hands have anything special. They're made of matter like everything else. And any object I bring near the straw will attract it by electrostatic induction. And how that works is any material we bring near a charged object, the like charges will be repelled away, the like charges will be attracted near, and within the object there will be a slight separation of charge that we call induction, and induction is always an attractive force. So, that's the second one, and it was shown to me by a student in Paris, France. So far, we've seen a little bit of science, maybe a little bit of magic. Now it's time for a little bit of art. So for this part, I want 2 volunteers to come on stage who want to draw a picture for me. So I'm going to bring out a big piece of paper. Yes, 2 big pieces of paper. And the first volunteer, I want someone who likes, I didn't pick you yet, but you're very eager. So you'll be the first volunteer. And I guess you'll be the second. Okay, they've picked themselves. Does one of you like the color yellow? No? Neither of you like yellow. Can I get a volunteer who likes yellow? Okay, there in the third row. Come on up. Thank you. And I'm just going to turn this around so the audience can't see while you're at work. So come on over here and draw a picture as big as you can on this paper. And while she's busy drawing, the 2 of you, you're going to need to work together and make a combined picture on this one. So come on over here. And with these 4 colors, both of you draw on this one. And draw nice and big so it takes up the whole screen. So we'll just give them about a minute or 2 to make a drawing there. So there's not too much pressure staring at the young artists at work. I'll show a really quick experiment in the meantime to give them some time to draw. Here's one that I learned from a friend in England about air pressure. So here I have a hollow tube. Air can flow through. A red balloon and a yellow balloon. I'm going to blow up these balloons. And just connect them with the tube. And I'm going to ask everyone to make a prediction for this one again. Science is all about predictions. Okay, first of all, which balloon is bigger, the red one or the yellow one? The red one is bigger. Which one has more air in it, the red one or the yellow one? The red one. Which one has a higher pressure? I heard some disagreement. Some say yellow, some say red. It'd be interesting if there's a way to test this. So, there's a principle of fluid dynamics. Fluids will always flow from high pressure to low pressure. So if I let go of the balloons and I let air flow, whichever one has the higher pressure will empty air out into the other one. So I want everyone to predict if you think air will flow from the red to the yellow or the yellow to the red. So put up your hand if you think it'll go from red to yellow. Okay, and if you think the air will go from yellow to red, put up your hand. So more people think red to yellow. Let's try it out. That didn't go right. One more time. Okay, so which has more air, the red or the yellow? Red, okay. So let's see which way air flows. From yellow to red. Now, the reason that happens is because as you stretch out the balloon, it gets thinner in this direction and thinner in this direction. So the elastic force to pull it back in gets weaker. You add more air, but as the balloon gets thinner, it can't stretch as hard and the pressure goes down. So the balloon with more air in it was actually at a lower pressure than the balloon with less air. And if you've ever blown up a balloon yourself, you'll be familiar with this. The hardest breath to put in is the first one, right when the rubber isn't stretched at all. And to get it stretched thin, that takes more pressure to fill it up. So this balloon with less air is at a higher pressure than this with more air. And the artist, it looks like you're done. Perfect. So, I'll get you to come stand on this side, and I'll ask that we can turn the lights off and that we can turn the screen off so we can fully appreciate this artwork in all its beauty. And I want you to pick, do you like the color red, blue, or green? Red, okay, red. And this is your picture, right? Okay, so let's look at your picture. Oh, and can you guys actually, you'll each take a red light. No, red light, just leave it red. And I want you to show her beautiful picture in the red light. You had several minutes. Where's your picture? You were supposed to draw me a picture. Okay, let's see. They at least drew something? Okay, let's see. If okay, so your picture's not there, but try pushing lightly on the light to change color. Oh, there's your picture. So what happened? Where her picture went? It's not magic, it's science. So if we go back to the red light for a second, and actually I'll grab these lights and I'll get you guys to sit back down. So can we applaud them for their drawings? And we'll get... Oh, thank you. Okay, so I'm going to move the yellow one right to the front at first. So we can see the pictures there, but then it appears to disappear. And this shows the principle of fluorescence. So the marker is a fluorescent highlighter. What that means is it fluoresces, but what it means to fluoresce is it re-emits light of a lower energy than what was incident. So we see blue light has more energy than yellow. If we go over to the red light has the least energy of all, so it can't make the yellow fluoresce. We don't see it at all. Now here, the other drawing, we have several colors here. So we can see, and in the white light we'll see we have pink, blue, orange, green. And we can hopefully find out a little bit more about different energy levels of color. So we already established blue has the most energy. Red has the least. Blue can make yellow, orange, green, and pink fluoresce. They can all fluoresce in that. Now if we look at the green can make the orange and the pink fluoresce, but the green and yellow ink, those aren't particularly bright, so we know green has more energy than orange. So we can say, just from these simple pieces of artwork, we can say we know blue has the most energy, then green, then orange, then red. That's not all of the colors in the spectrum, but we can at least get an idea for how energy is spread out within the spectrum of light just by making a couple of colored pictures. So let's give another round of applause for the volunteers. And we can turn the lights back on for the next experiment. The next experiment, I'm going to use these rolls of toilet paper. And this is one where everyone in the audience who wants gets to participate as well. So if you want to follow along with this one, you need 4 sheets of toilet paper, 1, 2, 3, and 4. And I'm going to throw a couple of rolls of toilet paper, so get ready to catch it. Don't get it in the head. And just pass them around. Anyone who wants 4 sheets of toilet paper, grab 4 sheets of toilet paper, pass the roll along. Okay, so once you have some toilet paper, pass it around so everyone else can get some. Once you have it, hold it up so that I can see which parts of the room have toilet paper. And a little bit of background on this one while everyone's getting served. So These toilet paper experiments come from a good friend of mine in Bulgaria, a fellow teacher named Nasko. And he started doing toilet paper experiments when schools were closed because of the COVID lockdown. And just like I did from Paris, from Sofia, Bulgaria, he started having online lessons for students and families to do experiments with things around their house. And in Bulgaria, just like in France, everyone's got toilet paper at home. So he did a lot of experiments with toilet paper. Now, can everyone who has toilet paper hold it up so I can see? Okay, so most of you have toilet paper now. If not, keep passing around. And I want everyone to take one sheet. So we're just going to start with one sheet of toilet paper. And I want you to notice a couple things about it. One side is longer than the other side that's shorter. The shorter side has little bumps on it. The long side is smooth. And to start off with, I want everyone to hold it out with the short side up at the top with the little bumps. And I want you to take one hand and make an L. So an L like this, and grab the paper near the middle. Then the other hand, an L, grab it near the middle. And on the count of 3, I want you to pull one hand back, the other hand forwards, and try and rip the paper down the middle. 3, 2, 1. And I can see everyone ripped it pretty cleanly in half. You guys are good at ripping toilet paper. Well done. Now, take another piece of toilet paper, but hold it the other way around so the long side is on top and the short side is on the side. Then same thing as before, make an L, grab it near the middle, make an L, grab it near the middle. Looks like everyone's just about ready. On the count of 3, we're going to rip it again. 1, 2, 3. What happened there? So none of you managed to rip it all the way through. And that tells us about the structure of toilet paper. It's got a directionality of the fibers. The fibers run long ways, like the long pieces we were able to rip. The fibers run all the way down the length, but they don't run across this way. And that happens because of how toilet paper is made. What's toilet paper made from? I heard paper and trees, so it's a kind of paper. All paper is made from trees. Well, almost all paper. Toilet paper anyways. Does this look like a tree? No. So they do something to the tree. And what they do is they cut it down first, of course, but they chop it up into wood pulp. It's kind of like a tree smoothie. So it's like this mess of like liquidy fibers everywhere, but then they squeeze it down. And to make a long roll of toilet paper, they squeeze it through rollers that press it, and it gets pushed out in a long layer. On that extrusion process, that makes the fibers line up with the way it's gone out along the length of the whole roll. So we can see that with this simple demo. Now I want you to take one more piece of toilet paper. So this should be the third of 4 pieces. And I want you now to fold it up. So I'm just going to fold it gently in half several times. And I'm not going to twist it around at all. So don't twist it like that. Just fold it gently. So it's a small pack like that. There's not an exact way. Don't worry about an exact number of folds. Just so that it's small. kind of the size of a pen or a pencil. And once it's ready, hold it up like this so I can see when everyone's ready. Looks like most people. Let's give it another 5 or 10 seconds. Okay, and when you're ready, I want you to hold it tight, and on the count of 3, we're going to try and pull it apart. So everyone ready? 3, 2, 1, pull. Pretty easy, right? So the fibers aren't that strong. We can rip it apart. Now, take your last piece of toilet paper. So the 4th piece of toilet paper, and instead of folding, I want you to twist it. So twist and turn and make it so it's all twisted together, and do as many turns as you can. So get it twisted really tight. And it might kind of curl up on itself. If it does that, just pull it straight afterwards. So you want it wound up really tight. And again, once it's ready, hold it up in front of you so we can see when everyone's ready. And it takes a lot of twisting. So take an extra 10, 15 seconds. Make sure it's twisted a lot for this. Okay, and once it's ready, again, hold it up in front of you. And on the count of 3, you'll try and pull it apart, just like before. 3, 2, 1, pull. And you can manage to do it, but it was a lot harder than before, right? And if it's not harder than before, you didn't twist it enough. If you twisted it, it gets a lot harder. And what's going on there is once it's twisted around, the fibers press on each other, because as you twist it, it gets harder to press and gets tighter and tighter, and the fibers are pressing on each other. And because they're pressing hard, they increase the amount of friction, so it needs to overcome a lot of friction to pull the fibers apart. And so that's a couple of things we can do just with 4 sheets of toilet paper to understand a little bit more about this everyday object. So now we're getting near the end of the show. So I'm going to show you my all-time favorite experiment. And this is one that I came up with myself when I was volunteer teaching in Peru. Oh, and we'll need the hot water for this, so if we can put the kettle on. Yeah, they seem to be working on the kettle for me there. So, like I said, I travel around looking for new experiments, and I look for different places I can share those experiments. And I was in a relatively poor school in Cusco in Peru, and there wasn't any lab equipment. And I set myself the challenge of trying to make as much lab equipment as I could out of things I could get for free or very cheap. And so I thought about a thermometer, and that was the hardest one to do. So I'm going to show you my beer bottle thermometer. All I need for this one is an empty glass bottle. This is one I got here locally last night. I have a drinking straw, just like I use for the static electricity. This is a cork, like a laboratory cork to close bottles, just with a tube out of it so it's the right size for the straw so it can all fit together. And the last 2 things, a balloon. So I'm going to use the orange balloon and some colored water. So what do I have inside this bottle? Air. It's full of air. It's also full of potential, but it's full of air. And what happens to air when we change the temperature? So I think I heard some like it gets bigger, smaller, it expands, things like that. So it expands, but the problem is when we heat it, but the problem is we can't see air. Air is invisible. So that's why we're going to use colored water and a balloon to hold it. So I'm just going to put the balloon in the top of the bottle. And I'm going to go over to the table so they can get a close-up of me a little bit better. So balloon in the top of the bottle, and then I'm just going to fill the balloon with colored water. Okay, and we can see, and it's kind of small, so you can see better on the screen there. But we have the level of the water there. And it doesn't have any numbers yet, but it's already ready to test out as a thermometer. We just need some heat. So we're getting the kettle warmed up, but in the meantime, we can generate our own heat. So I want everyone to put your hands together and just rub them. And you'll be able to generate some heat. And that's more than enough heat for our thermometer. So I'm going to get 2 volunteers on stage. I want to see people who are rubbing their hands really hard. So if you want to be the volunteer, hold your hands up really high and rub them hard. Okay. Oh, and come to this side of the table so everyone can see. So come to this side. Okay, and rub your hands, get them nice and hot, and then put them on the bottle, and we'll see if we can get it to go up. So whenever you're ready, and it started all the way down here, we can see it's rising, it's rising. Look at that, let's give them a round of applause. So thank you, and now you can go sit back down. Okay, and in the meantime, I think the kettle's almost ready. So that's a proof of concept. This can work and the level can go up and down. We don't yet have any numbers on the thermometer. So to make it more like a real thermometer, we want numbers. And to do that, I'm going to use a bucket of cold water and a bucket of hot water. If we got it changing this much just with our hands, we need a longer straw. So I'm going to use this one here. Excellent, thank you. Okay, so now this is a lot bigger, and I'm going to put it in the cold water at first. It's going to go down, 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 and if it gets too low, I'm just going to add a little bit more water. This water feels like it's about 20 degrees. I'm going to measure it with the thermometer, which is sitting in there. Yeah, if you want to hold the thermometer so, like this one. And if it stopped moving, if you can tell me what temperature this water is, that'd be perfect. Okay, so that's about 19 degrees, and that's going to be when the water level is about the same level as the stopper there. And now I'm going to make water that's about 50 degrees. So I'm going to take some of this water, just so we have a little bit more in this bucket, and the boiling water. And 50 degrees was actually described by Isaac Newton, famous physicist, as a temperature in which you can put your hand in a hot bath and it won't burn, but you don't want to keep it there more than about 3 or 4 seconds. So that feels like it'll be close to that. 46? Let's go with 46 and we'll see how high this thermometer gets. And as we're waiting for it to go up, once we have the highest and the lowest point, all we need to do is measure the distance between the two and mark every degree, and then we can use it as a working thermometer. Do you have an extra hand to hold this while I get the tape measure? And that's the final part of the pendulum from the first experiment now being used. And if we measure, so between 19 degrees and 46 degrees, that should be a difference of 27 degrees. That difference corresponds to 39 centimeters. So each degree Celsius should be 39 divided by 27 centimeters high, or about 1.3 centimeters. So the only thing left to do if we wanted to use this as a thermometer is just mark every 1.3 centimeters, and then we have a working thermometer. So that's been my all-time favorite experiment, because as I've traveled around, I've visited a number of schools in less wealthy countries where they don't even have thermometers in the lab, but you're able to make your own lab equipment if you use a little bit of science for it. This has been a preview of some of my very favorite experiments that I've gotten around from around the world. I hope you've enjoyed them as much as I've enjoyed showing them to you.
Если у кого-то есть какой-нибудь вопрос, можете руку поднять. Давайте 2-3 вопроса возьмем.
Which countries did you go?
Over 40 different countries. Should I start naming ones off? I'm sure I'll leave one or two out.
Maybe not all of them.
But
The
so,
most exotic ones, maybe.
Kazakhstan. Another particularly exotic one where I go every year, sometimes twice a year, and I've even brought students, is Ghana in West Africa. And for me, that's a really exotic one because the weather's always hot. It's very different than things are in Paris. But I've also been to Cambodia, where I did volunteer teaching there. I've been to Peru and Argentina. I'm going to Mexico for a conference in November. They've invited me to perform there. But most of the places I've been to have been ones I can travel to by bicycle. So from Paris, I've been to almost every country in Europe. Like I've been to Portugal, Spain, Andorra, France, Germany, Netherlands, Belgium, Denmark, Sweden, Finland, Estonia, Latvia, Lithuania, Poland, Slovakia, Hungary, Serbia, Bulgaria, Romania, and Turkey. That was all within 1 year in 2018. But also most of the others I've been to on, like most of the other European countries I've been to on other trips. Again, mainly by bike when I have the time to do so. Because that way I get to small places, I get to see schools where people wouldn't necessarily otherwise go if you're just flying in and flying out of somewhere.
Yes.
Как ты научился говорить по-английски?
Well, the question is, how you learn to speak in English?
So I actually didn't understand most of the introduction before I came on stage, so I'm not sure if you were told that I grew up in Toronto, Canada, speaking English, because it's an English-speaking part of Canada. But now I'm based in France, so I learned that afterwards. I also speak Spanish and Italian, but that's not necessarily that useful in Kazakhstan.
Which scientist taught you the best trick?
Oh. There's a lot of ones that come to mind, but the very best one overall was someone named Paul, who used to work at the Exploratorium in San Francisco. And not only was he a great scientist, and he knew lots of experiments, and he came up with new ones all the time, but one of the most special things about Paul was when he'd meet teachers, and they'd tell him about an experiment or an idea for an experiment, his face would just light up, and he'd smile, and he knew exactly how to encourage people to make new experiments and to be the best teachers they could. And so he was one of the people who inspired me to keep learning from other people and to get better at teaching myself. So probably Paul is my favorite overall, but there's a lot of great people I've met.
Супер. Последний вопрос.
Hi. My question is, how did you develop your career in science? How did you start your journey in your life?
That's a really good question. And I could spend hours talking about it, but the short version is that I started teaching science as a way that I could live in different countries. I grew up in Canada. I wanted to live in Europe. I wanted to travel. So I started that way. And then once I'd been teaching for a long time, I realized there were a lot of different ideas in different places I had been. Growing up in one place, moving to another. There were a lot of different ideas, and so I started thinking, wouldn't it be interesting to gather the ideas of how people teach from all these different countries? And so more and more in my spare time, like there's a lot of school vacation in France. There's 2 months in the summer and 8 other weeks throughout the school year. And anytime I had time, I traveled to learn more experiments. And after several years of that, people started inviting me to do trainings for teachers, invited to more schools, invited to festivals like this. So it was really from that curiosity, just wanting to learn more myself and learn more, not only about science, but about different cultures, different countries, and things like that.
Amazing. Thank you, Michael. Thank you very much.
Oh, thank you.
Yeah, I hope you enjoyed as well.
Oh, yes. Oh, and a big thank you to everyone doing the translations as well, and everyone helping out backstage, too.